The derivative. We've spent a couple of class periods now talking about the derivative, and this video is meant to kind of follow up on that discussion and show just a few more examples of sketches and how the derivative relates with respect to its definition. Remember, the derivative can be defined really in two ways. First, as the slope of the curve at a point, but you can also think of it as the slope of the tangent line, the linear function, the tangent line to the curve at a point. And so we'll look at some graphs first, and then we'll look at some algebraic manipulations, finding the derivative using the difference quotient, as we've talked about in class. So let's start with this first graph here, f of x. Well, f of x appears to be a downward-facing quadratic. And I've labeled 4 different points, A, B, C, and D. And I want to talk about the derivative at each of those points and compare it to the derivative at the others. Recall that the derivative is the slope of the tangent line. So if I drew a tangent line, remember a tangent line is one that you can think of it as bouncing off or intersecting the curve exactly once versus a secant line, which intersects it more than once. The slope of the tangent line there is clearly positive. And if we were to compare it to the slope of the tangent line at B, we would say that the slope of the tangent line at A is greater. So we might say that f prime of A, maybe I should call this x value A, and this input B, and this one C, and this one D. We could say that f prime of A is definitely greater than 0, and it's also greater than f prime of B. It's bigger. Now the slope of the tangent line at C is intended to be 0. We can see that the curve changes direction there. It's continuous. It's a nice smooth curve. Changes from increasing to decreasing right at C. And so we could say that f prime of C is equal to 0. F prime of D, on the other hand, the slope of that tangent line is negative. So we would say that f prime of D, for example, is negative. It is less than 0. Let's move on to g of x. So here I've labeled 1, 2, 3, 4, 5 inputs. Again, we'll call them A, B, C, D, and E. So I intended for you to think of those as x values, as inputs. And so we want to find the slope at each of those points. Well, I hope you recognize that the slope at A is quite negative as compared to the slope at B, still negative, but less negative. They're both less than 0. But we would actually say in this case, if you think about it, we'd say that f prime of B is greater than f prime of A because f prime of A is more negative than f prime of B. Again, f prime of C in this case, just like we saw over here, we've got a change of direction on this nice smooth curve. We're going from decreasing in this case to increasing, and so we could say that f prime of C is 0. F prime of D is slightly positive, whereas f prime of E is a little bit more positive. So we could say that f prime of E, for example, is greater than f prime of D. Last but not least, we've got some ordered pairs here. Again, we've got in this case 1, 2, 3, 4, 5. I've got 6 ordered pairs, 6 points on the curve. And I think by now you could tell me the sign of f prime of A. F prime of A is positive. F prime of B is 0. F prime of C is negative. The one unique case I want to talk about here, though, is f prime of D. We would say that at this point right here, which we're soon going to be talking in detail about, called a point of inflection, okay, we would say that f prime of D is where this section of the curve has the most negative slope. In other words, the slope is negative here, it's negative here, it's negative here, but it's actually most negative here, right where we change concavity. The slope, the derivative, is still negative there, it's still negative there, and it's still negative there, but you can see, I hope you can see that it's getting less negative. The slope is getting less negative. The function is still positive, it's above the x-axis, but the slopes are getting less negative as we approach this ordered pair E, where again, f prime of E is equal to 0, just as f prime of B is equal to 0. And now the derivative becomes positive because the function, the function is increasing. And at f prime of f, were a little more positive than these other ordered pairs. And we'll talk in more detail about that as we progress through the course. But I want to just point out the fact that f prime of d, on this interval here, f prime of d is where the derivative is most negative. All right, let's look at some algebraic justifications of the derivative. So the goal here is to compute, not to estimate, but to compute f prime algebraically. And we're going to use the difference quotient. So we'll use the difference quotient to compute that. Now, once we've computed that using the difference quotient, we'll find the equation of the tangent line, just as we've done in class, to the function at that point. So let's start with f prime, let's start by finding f prime of 3. After all, that's the goal. It says compute f prime of x algebraically if f of x, the original function, is negative 3x squared at x is equal to 3. Now, it is helpful, I think, to sketch this. I may not sketch every single one of these for the sake of time. But we know that f prime, that if f of x is negative 3x squared, then we've got a downward facing quadratic which goes through the origin. Okay? And if we want f prime of 3, then what we want is at x equals 3, we're trying to find the slope of the tangent line. F prime of 3 is whatever the slope of that line, that tangent line is. And once we've got the slope and we have an ordered pair, we can find the equation for the tangent line. So let's find f prime of 3 using the limit definition of derivative. Recall that the derivative is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. And we've talked in detail about what that h means. We're trying to, as h approaches 0, the two ordered pairs are approaching each other, and so the secant line is essentially turning into the tangent line. Now, if f of x is negative 3x squared, then we've got the limit as h goes to 0 of negative 3 times the quantity x plus h quantity squared minus whatever the function evaluated at 3 is. So we put 3 in here. 3 squared is 9. 9 times negative 3 is negative 27. So subtract negative 27, all divided by h. Now we've spent a great deal of time discussing shortcut for squaring that binomial. So recall that if I'm squaring that binomial, then I've got the limit as h goes to 0 of negative 3 times the quantity x squared plus 2xh plus h squared. And then we've got plus 27 divided by h. Of course, I forgot to put x in, didn't I? I should have substituted 3 for x. No reason to wait. So let's put a 3 in there. Okay? And I should have put a 3 in here. And the reason, again, that we're putting 3 in is because we're evaluating this at x equals 3. Now, we've got the limit as h goes to 0 of negative 3 times 9 plus 6h plus h squared plus 27. Oops, I'm sorry, the parenthesis goes here. All over h. Distribute our negative 3. This is now the limit as h goes to 0 of negative 27 minus 18h minus 3h squared plus 27 all over h. Negative 27 and positive 27 cancel. The word is cancel there. The verb is cancel. We'll factor out an h, and we're left with negative 18 minus 3h in our numerator. Now, these h's reduce. The verb there is reduce. H over h is 1. And we've got the limit as h goes to 0 of negative 18 minus 3h, which means we can finally substitute 0 in for h. Okay? And we are left with a derivative of negative 18. In other words, f prime of 3 is negative 18. In other words, at x equals 3, at this ordered pair right here, the slope of that line is negative 18. Now we've got a slope. We need an ordered pair. We already know that the input of the ordered pair is 3. We already had to find the output of the ordered pair. There it is, negative 27. And so the equation of this line right here that we've drawn is y minus negative 27. That's y minus y1 is equal to m, negative 18, times the quantity x minus 3. Of course, y minus negative 27 is y plus 27. So we've got y plus 27 is equal to negative 18 times the quantity x minus 3. And as I've mentioned before, it is completely acceptable to leave this in point slope form. If you really wanted to convert it to slope intercept, you could go ahead and do that, but it's completely acceptable to leave it in point slope form. For our next example, we've got f of x is equal to x squared minus x. And this time we're at x is equal to negative 1. Now I would encourage you to plot this curve and draw your tangent line just so that you know what's going on. But for the sake of time, so I don't have to pause and get out my calculator, let's go ahead and get to work on the limit definition of derivative. So we are looking for f prime of negative 1 first. F prime of negative 1 is the limit as h goes to 0 of f of x plus h minus f of x over h. Okay. Again, x being negative 1. So if we substitute negative 1 into the function, we get negative 1 squared, which is 1. Okay. Minus negative 1, which is another 1, we get 2. So our output for the ordered pair is 2. Now, we have to put x plus h in wherever we have an input into our original function. Because again, we're evaluating f of x plus h. X is negative 1, so negative 1 plus h, quantity squared, minus negative 1 plus h. There is f of x plus h. There is f of x. Again, where x is negative 1. Okay, so we've got some algebra. The setup is often the hard part. Now we do the algebra. So negative 1 plus h quantity squared is the square of negative 1. That's 1. And we've got minus 2h plus h squared. We distribute this negative 1. We get plus 1. And then it's going to be a minus h all over h. Now, and I just realized that I forgot my minus 2. So there should be a minus 2 tacked on the end there. Now, 1 plus 1 minus 2 cancels. That's 0. We can factor, or actually we can combine these like terms. So negative 2h minus h is negative 3h. So we've got the limit as h goes to 0 of negative 3h plus h squared over h. We can factor an h out of our numerator. The h is reduced. We can finally substitute 0 for h right here, and we're left with negative 3, which means that the derivative, f prime of negative 1, is negative 3. The slope of this curve, x squared minus x, the slope of the curve at x equals negative 1 is negative 3. In other words, the curve is decreasing at a slope at a rate of negative 3 over 1. Now, last but not least, we do want the equation of the tangent line. To find the tangent line, we're going to say y minus our output. Okay? And recall that our output was, 2? Okay? Y minus 2 is equal to m negative 3 times the quantity x minus, and in this case is going to be negative 1. We've got to subtract negative 1 because, again, the ordered pair that we're looking at was negative 1 comma 2. I got that ordered pair by substituting negative 1 into the function. So negative 1 squared is 1, minus negative 1 is plus another 1 that gives me 2. So clean this up. Point slope form, y minus 2 is equal to negative 3 times the quantity x plus 2. And again, that is the equation for our tangent line. The line tangent to the curve x squared minus x, specifically at x equals negative 1. Let's look at one more. Compute f prime of x algebraically, and then find the equation of the tangent line to the Find the equation of the tangent line to the curve, that should say, really, at that point. So f of x is x to the negative second. Now recall that x to the negative second is the same as 1 over x to the positive second. You can jump the line, change the sign of the exponent. The line I'm talking about is that fraction bar. It's the same as 1 over x squared. We want it, and I apologize for changing screens, we want it at x equals 6. So x to the negative second, or 1 over x squared, looks like this. And we want the equation, first the slope and then the equation at x equals 6. So again, we're looking for that tangent line, the equation of that tangent line. Now, we need an ordered pair, and then we need to know the slope of this line. So let's start with our ordered pair. Our ordered pair has an x value of 6. That's given, 6. It has a y value, or an output, of whatever comes out when I put 6 in. So when I put 6 in here, 1 over 6 squared is 1 over 36. So there's our ordered pair. When we go to the tangent line equation, we're going to say y minus 1 over 36 is equal to m, which we're going to have to find. Remember, m is our slope. That's f prime of 6, okay, times the quantity x minus 6. So we need to find m, and we're done. M is the derivative. So f prime of 6 is what we're solving for. F prime of 6 is equal to, again, the limit as h goes to 0, of f of x plus h, so that's 1 over x plus h quantity squared. You put x plus h into this function, okay? That's f of x plus h minus f of x, which is 1 over x squared over h. And I apologize, I did it again. I like to substitute. Technically, the order doesn't matter, but I should have substituted my 6 here and here. I like to do that personally. I just forgot. So we can write then the limit as h goes to 0 of 1 over 6 plus h quantity squared minus 1 over 36 all over h. Now we need a common denominator, so there's some work to be done. I'm going to multiply this by 6 plus h squared over 6 plus h squared, which is a fancy way of multiplying by 1. And I'll multiply this by 36 over 36, which is also a fancy way of multiplying by 1. So now we've got the limit as h goes to 0 of 36 minus 6 plus h quantity squared over 36 times 6 plus h quantity squared. There's that common denominator, okay, that we found on purpose, over h. Now, this h, and we've talked about this in class before, this is the same as dividing this by h over 1. And if we divide that by h over 1, it's the same as multiplying by 1 over h. So, fastest way to think about it is h becomes part of your denominator. So now we've got the limit as h goes to 0 of 36 minus 6 plus h quantity squared over 36 times h times 6 plus h quantity squared. We can square this binomial. Limit as h goes to 0 of 36 minus the quantity 6 squared, 36, plus twice 6 times h, so it's going to be plus 12h, plus h squared, all over 36h times 6 plus h quantity squared. Now, distribute the negative. We're getting close. Limit as h goes to 0 of 36 minus 36 minus 12h minus h squared all over 36h times 6 plus h quantity squared. Okay, 36 take away 36 cancels, that's 0. We can factor in h out of both of these terms. We now have the limit as h goes to 0 of h times the quantity negative 12 minus h over 6 plus h quantity squared times 36 times h. These h's reduce to 1, And we can actually, if you look carefully, you can put 0 in for h now, because if you put 0 here and 0 here, you're not breaking any rules. So what we have it finally is negative 12 over 6 squared, because you put 0 in for h here, so that's going to be 6 squared times 36. Well, that's the same as negative 6 times 2. Let's see. Over 6 times 6 times 36. The 6 is reduced. 2 over 6 reduces to a third. And we're left with negative 1 over, let's see, 108. 36 times 3 is 108. So that's your slope. That's f prime of 6. And so put it all together now. Recall up here, we said we're solving for m. Once we have m, we're in business. So our final tangent line equation then in point slope form would be y minus 1 over 36 is equal to negative 1 over 108 times the quantity x minus 6. You could again clean that up, or I should say you could convert that to slope-intercept form, but point slope is just as good. All right, the final item I'd like to talk about is going to come up a couple of times throughout the course, and we're dealing specifically here with even and odd functions. Now, an even function is reflection symmetric, recall, over the y-axis. Look at all 4 of these examples here. They're all reflection symmetric over the y-axis. In other words, if you took this side and reflected it over here, you'd get that. Took that and reflected over here, you get that. If you reflected your function over the y-axis, you would get the exact same function that you started with. We also say, you've probably heard before, f of negative x is equal to f of positive x. Even functions, in other words, if you go to opposite inputs, choose any 2 opposite inputs, we'll call this x and negative x. If you go to opposite inputs, you will get the same outputs. Okay, and that's true in all of these cases. You go to opposite inputs, you'll get the same outputs. So f of negative x is equal to f of positive x. Now, if you look at these functions, though, let's focus on the negative x and positive x and think about their derivatives for a moment. Look at these functions, and look at the slope of the tangent line to the curve there compared to the slope of the tangent line to the curve there. Or look at the slope of the tangent line to the curve here compared to the slope of the tangent line to the curve here. Okay? Same thing here. This ordered pair and this ordered pair. So in other words, I'm at opposite x values. We'll call this x and call this negative x. Call this x and call this negative x. And what I hope you'll notice is that their slopes are actually opposite. So for even functions, this is true with respect to the function itself, but with respect to the derivative, the derivatives, the slopes of the tangent lines of the curve, the derivatives are opposites. So if I told you that f prime of x was 3, then you would say that f prime of negative x must be negative 3, and vice versa. Okay, so they're opposite x values, opposite inputs, opposite derivatives. Okay, so we could say f prime of negative x is equal to the opposite of f prime of x, would be one way of saying that, if f of x is even. So some examples of even functions. I intended for this to be x squared, that's even. I intended for this to be the opposite, or negative 1 over x squared, that's even. This could certainly be the cosine of x. There you've got your cosine curve. And here maybe we've got the absolute value of x reflected over the x-axis. All even functions. All right. Last but not least, and we'll close out this video, what if the function was odd? So here they're even, now they're odd. Odd functions are rotation symmetric about a very unique point, about the origin specifically. If you think of these 4 graphs, okay, I'm sorry, this is actually even. This one right here. So we can erase that because that's even. I intended to look at some odd ones specifically. Okay, but if we look at these 3 graphs, they are all rotation symmetric about that origin. If you rotated them 180 degrees, take this thing and spin it around 180 degrees, you're going to get the same graph you started with. Same thing here and same thing here. So here we have, for example, maybe 1 over x. Here we've got, I intended for this to be the sine of x, y is equal to the sine of x, and here we've got x cubed. They're all considered to be odd functions. Now, specifically, look at their slopes at opposite x values. So we'll call this x, call this negative x. The slope of the tangent line of the curve here is negative, and there it is, also negative. In fact, those lines are parallel. Now, when you have two lines that are parallel, their slopes are equal to each other. Let's go out to x and negative x. Look at the slope of the tangent line of the curve there. Look at the slope of the tangent line of the curve there. They're parallel. One more. Here's x. So we'll look at the slope of the tangent line of the curve there. And here's negative x. Negative x and x. Look at the slope. Look at the slope. Again, they're equal, they're parallel. And so, for odd functions, we can say that f prime of negative x is equal to f prime of positive x. In other words, opposite x values, the derivatives are the same. Now, with respect to f of x, because I also touched on f of x here, and f prime, with respect to f of x, if it's an odd function, we say that f of negative x is equal to negative f of x. In other words, the actual ordered pairs themselves, not the derivatives, but the ordered pairs themselves, if you go out to positive x and you go out to negative x, the actual ordered pairs, the y values are opposite. That one we go up some distance, that one we go down the same distance. Go out to x and negative x, the outputs, the y values are opposite. In other words, with respect to f of x, f of negative x is equal to the opposite of f of x. But with respect to their derivatives, it's an odd function, the derivatives of the opposite inputs are exactly the same. That's all I've got for this video.